A very warm welcome to our weekly paper reading. Today's topic is large concept models, language modeling in a sentence representation space. This paper came out from Meta, the FAIR Labs. It is very recent. It came out barely about, I would say, a couple of weeks ago. And I think it may go down as one of the more important contributions or interesting ideas of this year. The gist of this paper is to say that, see, when we use large language models with their architecture inherently, especially when we use the decoder-only architectures, which is quite common with these days, all the tasks, let's say summarization of tasks or answering questions or continuation and so forth, all the things that we are familiar with large language models, it does inherently through a next token prediction. The input goes in, the user input goes in, or the prompt goes in, and then the first token, at the end of it, the decoder produces logits. Those logits leads to, through a softmax, to a certain probability distribution, controlled by how peaked it is controlled by a temperature. And you sample off the distribution, some form of sampling, let's say nucleus sampling or something. And then you sample in order to bring in a certain degree of diversity to it. And so you pick one of the higher probable, most of the time, one of the higher probability tokens as the next token generated. And then you take the next token and append it to the prompt. And then, so it becomes an autoregressive causal model that is used to predict the next token and the next token and the next token. But the illusion is, and it's a very compelling illusion, that the machine is answering your question. It is one of the miracles that despite it being just a next token prediction engine, these LLMs are able to answer our questions or do whatever we ask it to do, summarizations and so on and so forth, with so much coherence. Nevertheless, they do suffer from hallucination, they suffer from bias, they suffer from other issues. So there has often been a feeling that one has to go beyond the next token prediction engine. Right? This basic dominant metaphor that we have today, which is that of next token prediction, which has often caused LLMs to be nicknamed as the stochastic parrot. Right? General feeling is this is probably not the way to AGI. This is not the way to make machines think about the input, reason properly. At the end of it, if at any given moment it's just predicting the next token, one is led to believe, despite the evidence, which seems to be fairly compelling, but one is theoretically led to believe that there has to be a better way. And so there has been a pursuit of a better way. One argument against LLMs in the standard way that we know it has been what people call, and what, for example, Jan LeCun calls, the diffusion of errors. Diffusion of errors is a concept that, see, if in the next token prediction, the probability that you'll make an error is 0.1%. By the time 100 tokens are generated, the probability that it is still not making an error actually becomes very small, because 99.9% to the power 100 is actually a vanishingly small number. So it means that sooner or later the machine will start drifting away, or so the thinking was. Now, over the last 2 years, we have seen that people have made these LLMs smarter and smarter, and they do a pretty good job of coming up with coherent responses. From a more theoretical perspective, people have been looking at alternatives to the next token generation approach. And this paper, this large concept models, is I would consider a very interesting breakthrough in this particular endeavor, to not have just a next token prediction engine. Another of its benefits is that computationally, it is a little, instead of reasoning at the level of a token, it reasons at the level of a concept. So the problem comes, can you predict the next concept? Now the question is, what is a concept? And here the authors reason like this. They say that, see, human beings, suppose you were to write a research paper, then you would first have an idea a grand idea what it is about. What is it that you do? And many of you who have all written research papers know the basic format: introduction, method, results, conclusion, and then references and so forth. So you create a big block outlines, and then you fill them up with smaller sort of themes and concepts. And so it's hierarchical planning or hierarchical reasoning. Now, in this paper, they take the concept, they bring up the concept, literally the notion of a concept. They say that we think in terms of concepts, and so the fundamental or the atomic unit, they call it a concept. Now, while the notion of a concept is broader, for practical reasons, they started with what may be a much simpler representation. They said, let's consider one sentence a concept. Then, when you consider a sentence a concept, they put a further limitation. If your sentence is sufficiently complex or long, then they would rather reduce it down to no more than a sentence of 10, at most 20 tokens. So that's, in other words, a simpler sentence. And the reason has to do with the fact that they are using a sentence encoder, Sonar, which is a multimodal encoder, which actually works across 200 languages, one of the more effective encoders that we have. And one of the merits of the Sonar encoder has been that it takes an approach that sort of is a precursor to it. It basically says that given a sentence in whatever language is written, it represents a thought. And let's create a thought vector, an embedding vector for that. That is language independent. And if it is language independent, then one could potentially decode that vector into another language easily. You could do a translation. Or if it is a thought, then you could perhaps, and so on and so forth. So you could do all the things that you do with a sentence embedding. So that's the basic idea. You start with a set of, then you see that if you take a text paragraph, you can now decompose it into thoughts, and simply put, into sentences. Once you have decomposed it into sentences, then instead of predicting the next token, you instead predict the next thought. What is the next concept? And once you have thought of the next concept, it's a simple matter after that to decode that concept back into text or words. Right? Now, this paper has a strong flavor of the JEPA. If you are familiar with the JEPA, IJEPA and VJEPA line of thinking, you will see that this paper, the way it approaches it, is quite reminiscent of that. Almost everything is done. The basic magic happens in a representation space, which is the sentence representation space. If you're familiar with sentence encoding or sentence embedding, which these days most of us are familiar with because of the RAG and semantic search and so on and so forth. So this would feel a very, very familiar territory. So what you do, and I'm giving the big idea before we delve into the paper, is that let's just say that you have a prompt. You take the prompt and break it up into the thoughts, into sentences or thoughts. Then you encode it. You give it to Sonar to encode it into each thought into one vector. Now Sonar creates a single vector representation. Now, if you remember the way the Sonar was treated, it's sort of an auto encoder. You try to decode it back into into the text, right? From the latent representation, you use a mean squared error loss function to see if it can, or reconstruction loss, to see whether the encoding is, or the representation is faithful, and it captures the whole meaning of the semantics of the sentence. So given that Sonar encoder, now you end up with, for all the thoughts of all the sentences, one vector. And that represents an order of magnitude smaller computational problem, because the LLM, for example, has a vector for every word piece, every token. Here you have a vector for every sentence, not for every token. So the granularity is different. And if you assume that a concept or sentence has 10 to 20 tokens, then you have at least one order of magnitude reduction in the sort of a sequence lens that you feed into downstream LLM, a decoder LLM into that. And that's the idea. So once you have that, what you end up with is a set of concept tokens, concept vectors, embedding vectors for each of the concepts or sentences. And then it becomes a problem of the standard decoder, a autoregressive causal model. So what is the next, in the latent representation space, what is the next vector that should be there? Right? And the next vector that should be there. And you can keep predicting the vectors in the latent space, and then you can decode it, use a decoder to create some text out of it. That's the basic idea. Now, in this paper, they use two approaches, or rather three approaches, but two principal approaches. One is the base large concept model, which is basically just using a decoder part of the transformer, the standard LLM kind of a reasoning, but working in the latent space of concepts. So fairly straightforward to understand. That is one approach. The second approach that they take borrows from image processing or computer vision. In computer vision, as you know, one of the most popular models has been the diffusion model. And so it borrows the diffusion model and it says, can we hybridize the diffusion model as the decoder in some sense of the next sentence, of the next concept, which of course we can then decipher into words. So the deciphering into words is a minor thing, and we will come to it. But the principal activity is everything is done in the latent space. So I'll just read the abstract of the paper, and then we'll sort of try to understand this paper in terms of the images that are there. The abstract reads as follows. LLMs have revolutionized the field of artificial intelligence and have emerged as a de facto tool for many tasks. The current established technology of LLMs is to process input and generate output at the token level, which is, of course, the next token prediction engine. This is in sharp contrast to humans who operate at multiple levels of abstraction. And I believe this contrast is worth mentioning, as well as beyond words, to analyze information and generate creative content. In this paper, we present an attempt at an architecture which operates on an explicit higher level semantic representation, which we call concept. And this is that's therefore the title of the paper, Large Concept Models. Concepts are language and modality agnostic and represent a higher level idea or action in a flow. Language independence is obvious. For example, if you say that a donut has a hole in the center, doesn't matter whether you say it in English or whether you say it in French or whether you say it in Hindi. Nevertheless, the idea is still the same, namely geometrically, a donut has a hole in it. Similarly, modalities don't matter whether you write it out or whether you speak it out, whether it's audio or text, it nevertheless conveys the same concept. And therefore, they say that it operates as an explicit higher level semantic representation. Concepts are language and modality agnostic and represent a higher level idea or action in a flow. Right? So this is how they define a concept. Hence, we build a large concept model. In this study, as a proof of feasibility, we assume that a concept corresponds to a sentence and use an existing sentence embedding space, Sonar, which supports up to 200 languages in both text and speech modality. Now, just something to mention. This is a research paper that opens a door. It says, is this idea even feasible? And they show that even a minimal implementation of it using a pre-existing sentence encoder, Sonar, does validate the idea. It does leave the door open that for the purposes of this line of work, if you want to continue downstream, they should probably create a much more optimized encoder whose entire task is to work optimally in the large concept model as a tool within the large concept model architecture. But they haven't done it in this paper. Continuing on, the large concept model is trained to perform autoregressive sentence prediction in an embedding space. And that is the most crucial thing. All the activity happens in the embedding space. This, of course, if you are familiar with JEPA, the IJEPA, VJEPA line of thinking, you know that much of the work in those papers too were done in the embedding space or the latent space. We explore multiple approaches, namely mean squared error regression, variants of diffusion-based generation, and models operating in a quantized sonar space. These explorations are performed using 1.6 billion parameter models and training data in the order of 1.3 trillion tokens. Now, it's worth reflecting that these are very small models. 1.6 billion parameter models are quite small models. 1.3 trillion tokens is a modest amount of tokens. I mean, it's large, but still very doable computationally. I suppose it must have been the computational feasibility to prototype this idea, to check out the feasibility of the idea. So this is sort of the early research breakthrough, I would say. We perform an experimental evaluation on several generative tasks, namely summarization and a new task of summary expansion, so the opposite of summarization. So finally, we show that our model exhibits impressive zero-shot generalization performance to many languages, outperforming existing LLMs of the same size. The training code, etc., are freely available. By the way, the license for this is MIT license, which is really awesome, because now we can take it, download it from the GitHub, and start playing with it. A few days ago, actually, it was unclear what the licensing is, but they have recently fixed that. Now it is clear that it's MIT license and we can use it and play with it. So I'll skip some of the introduction, but one paragraph is worth noticing, and it's a very long paper, so we won't get time to read every single paragraph. But one thing that they do sort of get their intuition from is this paragraph, in which they say, imagine a researcher giving a 15-minute talk. In such a situation, researchers do not usually prepare detailed speech by writing out every single word they will pronounce. Instead, they outline a flow of high-level ideas they want to communicate. Should they give the same talk multiple times, the actual words being spoken may differ. Right? The talk could even be given in different languages, but the flow of higher level abstract ideas will remain the same. Similarly, when writing a research paper or essay on a specific topic, humans usually start by preparing an outline that structures the whole document into sections, which they then refine iteratively. Humans also detect and remember dependencies within the different parts of a long document at an abstract level. If we expand on our previous research writing example, keeping track of dependencies mean that we need to provide results for each of the experiment mentioned in the introduction. Finally, when processing and analyzing information, humans rarely consider every single word in a large document. Instead, we use a hierarchical approach. We remember which part of a long document we should search to find a specific piece of information. So it just positions it that this is how we as human beings think about, right, let's say giving a 15-minute talk. And every single thing that you see in this paragraph is in sharp contrast to how LLMs, at least as a black box, they seem to work, right? So and this is the crucial sentence. They say, to the best of our knowledge, this explicit hierarchical structure of information processing and generation at an abstract level, independent of any instantiation in a particular language or modality, cannot be found in any of the current LLMs. See, at this moment, there is no explicit work that says that internally such abstractions have been created. Though we do suspect that from the efficacy of the modern LLMs, the frontier models, that maybe somehow the LLMs have internally figured some things out, right? So if you guys remember, there was a different paper from Anthropic, which found a whole variety of sub-circuits within the LLM dealing with the concepts, right? But we'll park that for the time being. In this work, we present a new approach and so on and so forth. Let's go to the main idea, the paper. How does it go? So imagine that any sentence, so for the purposes of this paper, a concept is a sentence. Let's agree to that. And a relatively short sentence. If it is a big sentence, you break it up somehow into shorter sentences. Now, let's look at the figure on the left. If you look at the figure on the left, you figure on the left, Tim wasn't very athletic. He thought that would change if he joined a sport. He tried out for several teams. He didn't make the cut for any of them. He decided to train on his own instead. It's made up of 1, 2, 3, 4, 5 concepts. And if you say, suppose your task is summarization. Now, let us look at this a little carefully. Why am I not able to? Okay, so this is again, okay, obviously, give me a moment. Let me see why I'm not able to. Draw. All right, and yes, black. Okay, and one more second. Sorry, apologize. All right, so this is better. So if you look at this represents a point in some model dimension space, right? So what happens is that this sentence goes in, it goes into an encoder, the sonar. This sentence goes in, and what comes out of this is this point in some dimensional space, m-dimensional space. It comes out as a point. Likewise, the second one goes into the sonar, and it produces this point, the third one. So all of these, you're looking at, these points are in the embedding, sentence embedding space. And this is the space in which this entire paper does its work. Now, what it is saying is that if you look at this trajectory, the job of this large concept model is, let us say that your task is summarization. Its job is to go from this sort of purple arrows to this, to basically to these 2 points in the latent space. And those 2 points, if you decode it, as in you use a concept decoder back to saying what sentence could possibly correspond to this. Let me call this blue point A and this point B. The first blue point A and the second blue point B. Now you need a decoder to go back from concept to actual word pieces, right? And therefore to proper text in some language. So that text for the case of English would be, because he was not very athletic, Tim could not join teams to improve. So he decided to train on his own. If you read these 2 sentences, you would agree that it represents a summarization of the sequence of text, the sequence of sentences on the left, okay, the original sequence of sentences. And so the idea is this. Let us say that these are, so here, 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. There we go. So let's say that 5 particular sentences go in. So this boundary is where I'm drawing it out, are sentence boundaries. So you have words, words, words. So the first task is, given a text, you need to do text segmentation. You need to be able to break it up into sentences. Now, that is not as easy as we think. For example, if you look at NLP libraries of great maturity like Spacey does an amazing job of decomposing text into sentences, right? And figuring out the parts of speech and so on and so forth. Spacey, for those of you who have been using it, has been a workhorse of the industry for a long time, right? And for those of you who don't, just think of it as a tool which, amongst other things, can break up a text into sentences. However, it does have a weakness. Its weakness is that it is very heavily dependent on punctuation. It looks for full stops and question marks and exclamations and things like that to find or decipher the sentence boundary, and similar things in other languages. Now, there has been another model, a segment any text model, and that is less dependent on it. It's a more modern approach. Both of these can be used for text segmentation into sentences. So let us just assume that there is a tool that can break up the text into sentences. So now what do you get? You get sentences. Let me call these sentences 1, 2, 3, 4, 5. They will go into a sonar encoder. Sorry, sonar and sorry. What am I doing? I need to remove this touch. Okay. So they will go into a sonar encoder. A sentence, let's say a sentence goes in, some sentence goes in, and it produces a single vector. This is the point. Let's say that this sentence is 1, it will produce E1 vector, a vector E1. And this is important actually. Internally it does, like, as you know, if you're using a BERT-like architecture, when you feed in so many tokens that make up the sentence, or word pieces that make up the token, the tokens, for each token there will be a vector. So Sonar internally at the end of it uses an aggregation mechanism to take all of those embedding vectors for each of the tokens and then amalgamate to give you one single vector that should capture the entire semantics of the sentence. Now, those of you who are familiar with sentence BERT, the original research paper sentence BERT, you would remember all the familiar things. These are encoder-only models. These are often BERT-based, almost always, like BERT-based is very, very common. Encoder models, right? And you produce a single vector out of that. So that vector represents a bottleneck. Now, suppose you further require, as in the case of Sonar, that you should be able to decipher or decode back from the encoding vector to the sentence, and you use a mean squared error loss or some meaningful loss function. MSE would be the appropriate one, I guess. Then standard autoencoder kind of architecture. Then your decoder should be able to give you back that sentence, and therefore you have semantic sentence encoder. This makes even more sense when you insist that the decoding should happen in some other language. Right? And so that single vector becomes a bottleneck, in some sense, an information bottleneck. And if you remember, the information bottleneck principle says that when you constrain things, you put a bottleneck in a neural architecture, the neural architecture is forced in effect to grasp the semantics, the gist of the input, so that it's able to decode that from the bottleneck, decode it back. So that is that. So now this concept encoder, so it produces these vectors E1, E2, E3, E4, E5. And now the idea is that it will go into the large concept model. Think of the large concept model in the simplest case as just think like of a autoregressive model. So what happens is first all of these go in and it will produce the first vector. Let me just call it output 1. It will produce output 1 vector. And this is your standard decoder. Now this vector will comes back into this sequence and it helps you produce O2, which again comes in and helps you produce O3. So this is your, one can think of it as your basic autoregressive. And in the center, this large concept model begins to look very much like your LLM, that standard LLM, except that it is operating in a latent space, in an embedding space, rather than on the text space directly, or the token space directly, token vectors directly. Once you produce these vectors, these embeddings, concept embeddings, now the question is, you can pass it through the decoder half of this here is here, and you can get back your text. And that is the main idea that this paper brings about. This is what they are trying to say. And the amazing thing is that it does work. They have data, they have done experiments, and it does work very well. So now, how does it work? They have multiple approaches. So now this is a little bit important to read through. The main characteristics of a generic large concept model approach are as follows. 1, reasoning at an abstract language and modality agnostic level beyond tokens. So you can clearly see that if I can reduce a sentence to a concept vector, single concept vector, then obviously we are not working at the token level, right? Now, which is a big thing. you realize that you don't generate one token at a time. You're going to decode a single concept that you have predicted into a sentence, into a full sentence, right? So the granularity of generation changes completely. Also, it is language and modality agnostic for the same reasons that we talked about before. The LCM can be trained, i.e. acquired knowledge, in all languages and modalities at once, promising scalability in an unbiased way. Explicit hierarchical structure, better readability of long form output by a human being. So this is like basically they are saying that the output that comes out tends to be more readable because it's it's a sequence of concepts decoded. Facilitates local interactive editing by a user. So the user can go and, well, this is a claim that it opens the door to something like this. Handling of long context and long form output. So now here comes the interesting point. If you remember that the sequence length, so suppose you have, because you have a KQ in a product of, remember, I won't go through the whole thing, softmax, the times V, but this is a quadratic compute that has been the Achilles heel. It's basically how transformers work. But the main problem is because you have this inner KQ dot product, it means that it is quadratic in the number of tokens. So suppose I have 1,000 token, every token needs to pay attention to every other token and know the degree of attention is paying, right? It has to have an attention score between every token and every other token. That is an order n square compute, right? And so when you increase the sequence length or the context window, the transformers become increasingly complex, or the computation becomes more and more problematic, right? And now, of course, there are all sorts of techniques to ameliorate the situation, but this is the main issue that transformers have faced, which is why they're computationally heavy. Now, because you decrease you're not paying attention. It is not that every token is paying attention to every other token. Instead, every concept embedding is paying attention to every other concept embedding, right? So a concept is, as you can see, one concept is one sentence here, and a sentence has approximately 10 to 20 tokens. So it is at least an order of magnitude shorter, which means that your computation is 100, like 2 orders of magnitude smaller, right? In terms of, because it's quadratic in that, which is a big deal, they say. Unparalleled zero-shot generalization. They point out that because independent of the language or modality, the LCM is pre-trained and fine-tuned on, it can be applied to any language and modality supported by the sonar encoders. So you say that once you train this machine, the basic idea is that the machine is only working, the LCM is only working on concept vectors, embedding vectors, E2. These are the concept vectors. And these vectors, because Sonar works on 200 languages, so what it basically means is that your prediction is at the level, and multiple modalities, your prediction is at the level of concepts. So its only limiting factor of how many things it can support is the support base of the encoder and the decoder, the Sonar encoder decoder. Right, which is pretty wide because that prior work already works on 200 languages and many modalities. So it makes it essentially operate with equal flexibility across the range of languages, which is a huge thing. Right? And so they report results across that. The next point that they mention is modularity and extensibility. Unlike multimodal LLMs that can suffer from modality competition, concept encoders and decoders can be independently developed and optimized without any competition or interference. This is important. See, what happens is that when you mix modalities, you have a text encoder and you have a vision encoder, and their representations come. Now, which one gets higher, which the attention scores or whatever it is, there's always some, it doesn't quite equally work out. So there's some modality competition in typical LLMs. But here, because everything is reduced down to a concept vector, And is the concept vectors paying attention to each other? You don't have such a problem. Next thing is new languages or modalities can be easily added to for an existing system. What it means is that if you have an LCM model, then the encoder, all you have to do is make sure that your sonar encoder or its future variants, they can support your new languages. So long as they can support your new languages, essentially you have extensibility of the LCM for free, because LCM is the inner core of it. So now the goal of this paper is to provide a proof of concept of this high-level vision, etc. So we won't go into that. The main thing is, you got the main idea. So if you go back and read the Sonar paper, text embedding, the main idea was that you given a text, you use the old idea was that you would feed it and text embedding, and you would use a autoencoder, and mean squared error kind of a loss, and then so on and so forth, and you would decode it. You would do it for text and then use a teacher-student method, a form of distillation method, to then train the speech encoders also, like for other modality encoders also. This is the work done for Sonar, so we won't visit it. Suffice is to say that a text goes in, like if you give it one sentence, you get a sentence embedding, right? Which, if you're familiar with sentence BERT, etc., should look very, very familiar, except that it's a little bit more powerful than that. So now, if you look at it, by the way, at this moment, they haven't done this work for images and videos, but at this moment, this paper has limited itself to only speech and text, right? But for speech, it deals with close to 200 languages, which is quite impressive. And 76 languages, I suppose, for speech. And output currently is in only one. But output is in any of the 200 languages, and puts any of the 200 languages. They also mentioned that for vision, they have played with the American Sign Language. But actually, I didn't see any results pertaining to that. So now working through the paper, sentence segmentation, you can use spaCy or segment any text. Now, one of the results they showed is that if your text is very long, then it doesn't help. Your encoder decoder, so now performance goes down. So what they do is they cap it to, they create capped versions of spaCy segmenter and SAT segmenter. They call it spaCy capped and SAT capped, right? Which, this is the word here. They talk about it, cap. So they come up with a slightly different implementation. And the reason for that is they found that, see, when you take a very long piece of text and you treat it as a sentence, then semantically there are multiple thoughts, multiple concepts built in. And so it is not as effective. We know that the performance of these encoded sentence encoders degrades if you give it very long text. It is much better to give it shorter texts. So they do that. And they show that see, if you sentence size in characters, if you give it, then you will see that whether you use SAT or whether you use spaCy, the encoder decoder performance begins to drop significantly. On the other hand, if you just take short sentences, then the performances remain pretty high. Now, they do mention that in their experience, SAT capped is just slightly better than spaCy cap. spaCy is rule-based. SAT is more of a machine learning approach. So, well, that's that. Now, in this paper, they discuss 3 variants of how they go about doing large concept models. One is quite simple, the base one, which is basically saying, what is the base one? It basically says that, hey, first take your Sonar encoder, and for each of the sentences, come out with a concept vector. And then, so this is your concept vector here. And then what you do is, you do a linear transformation. So you would agree. So there's a normalized operation. Normalized operation, by the way, is just x minus mu over sigma, what people call the z-score, the z-vector. Right? So they do a normal scaling of that. And how do they compute the mu and sigma? They just look at the distribution of the distribution over the documents. Right? Sonar vectors, lots of sonar vectors, and where do they fall? You compute the mean vector, and then you do that. But nothing here, and then you multiply it by, if you remember, this is a space transformation, right? The point of this is you are transforming this sonar vector to a different space. This is a projection. you're projecting it to a different space in that, and then there is a post vector which denormalizes it and in effect projects it back into the concept space, right? So see, this concept vectors goes in, it gets transformed to a transformer decoder space, whatever the transformer decoder space is. So suppose this produces a vector of the model, R model, and this produces, I think they use the word sonar. No, this is the sonar. Post will go from sonar to D model. So yeah, this is it. This vector, a pre-vector, goes from the model to the sonar space. From sonar, you take it, you feed it to what this model will take, and then you have it autoregressively come up with the vectors, and then you post transform it back, denormalize it back into the next concept. And so you can give it the sequence of concepts and it will produce the next concept. This is pretty much it. There is nothing very complicated about it. It's your standard transformer decoder and it's the autoregressive model. So this they call their base LCM, right? The loss function, as you can imagine, a mean over all of their generations and the instances, nothing unusual. Then comes an interesting thought. The base model, therefore, gets you the core idea. But then they have an interesting idea that they play with. And they say, why not use diffusion models for this? Now, diffusion models have had a bit of a slow introduction to text space. They are much more common in the vision space, but it can be applied, partly because visions produce vectors in a continuous space, whereas text inherently have a certain discretization or a certain quantization there. So let's read through this. Diffusion-based LCMs are generative latent variable models. Just to whet your recollection on what a diffusion model is, diffusion models were trained like this. What you do is you take, one second, you take an image. Let's say that you take an image of hang on, I will, where is my pen's called? Draw. Yeah, let's take this. So suppose you have a dog. As you can see, that's a well-drawn dog. Now, what you do is you add, in the first step, you add an epsilon noise to it, a normalized Gaussian noise to it. So it will become a little bit blurry dog. And so you get a blurry image, and then you get a blurrier image, and you get a blurrier image. Till at the end of it, you can convince yourself that if you keep injecting noise, the noise will overwhelm the information, right? And so what you will end up with is just pure Gaussian noise at the end of it. Now the question is, if you do it in sufficiently many steps, and you ask this question, this is the forward diffusion. Yeah, and the idea comes from the fact that, see, one basic intuition is very physics-based. It comes from non-equilibrium thermodynamics, that if you put a drop of ink here, it has a well-formed structure. You can see the structure of the ink drop. But asymptotically, as it diffuses and time passes, the ink will be all over the place throughout the water, and you won't be able to see the ink anymore. All you will see is this. But between any two steps, let's say that you have this, an ink blob is like this, and in the next one, the ink blob is like this. You can ask yourself this question, can I reverse back to the original ink blob? Can I sort of reverse diffuse it? Right? This is the process of diffusion, forward diffusion. Can I train a neural network to infer from this more diffused state to the less diffused state? Right? Can I do this more diffused to less diffused state? And the way you do that is you sort of give it some conditioning. The way you do is that the reverse diffusion. So let's say that there's this thing, dog, and you keep on going, and ultimately you have noise. At each step, you can use, and I'm oversimplifying it a little bit, You can think of a unit, a basic autoencoder with residual links, a unit kind of a thing. But these days you do it with a transformer whose main job is to denoise it. It's basically a denoising autoencoder. Its job is that at each step, it will denoise. The forward process is that of denoise to this stage, denoise to this stage. Reverse process, you basically say that if this is a noisier version of the dog, can I use an autoencoder, denoising autoencoder like thinking, to get back to this stage? But you can do it conditioned on some caption. You can say a dog. So when you have a complete noise, how can you go back? Because you don't know what is left behind. And what you do is you keep conditioning it on text. A dog sitting, a dog sitting, or something like that. And so what this text does is the denoiser or the autoencoder keeps paying attention to the text. And because it continually, you basically say, look more like a dog sitting, look more like a dog sitting. Like the question that you ask is, what can I subtract? What noise can I subtract from this image so that it becomes a slightly more like a dog sitting? And ultimately what will happen is, once you have trained this network, you can start with pure noise. So reverse diffusion would be, you start with pure noise, but because you keep saying a dog sitting, and this thing is continually paying attention to this, dog sitting, it will go through the steps of gradually, ultimately ending up with some form of a dog sitting. Now, the interesting thing is a dog sitting can have many possible variations to it. And that is the generative nature of these models, because it is not that it's going towards one particular answer. It just has to produce an image that inherently looks like a dog sitting. In other words, if you take this image and you do a vision encoder, you create an embedding vector of this image, and you take the embedding vector of the text, a dog sitting, these two will be very close to each other. In other words, the distance will be, these two will be, the one and the other will be very close to each other, right? That is how diffusion models are trained. So now that's a sort of a detour into how diffusion model works. And I apologize that I gave a very quick sort of intuition into the diffusion model. It's a little bit more nuanced than that, but let's go with that. So in other words, if you keep telling the machine that it removes noise, that remove noise in such a way, a little bit of noise in such a way that it looks just a little bit more like a dog sitting. You can train a neural network to do that, to be conditioned on the information. And so there are ways of doing it. If you go back and read the original papers, there are ways of doing it with a classifier. There's a ways of doing it in a classifier-free way, etc. So one of the ways you do that is you just don't condition it in reverse diffusion. You say, okay, go just remove the noise, and it produces something. And then you say, okay, remove the noise, knowing that you have to move towards a dog sitting. And you now look at the image, and you take the two image vectors, and that gives you an intuition on how to make it even more look like a dog sitting. And that is it goes through the whole that's been part of the standard literature of diffusion models, but we won't get in. So this recaptures some of the old the whole theory. I mean, if you're familiar with this diffusion models, you'll be very familiar with these equations. But so for that reason, I'm not. I mean, if you're not, then I apologize. Probably my short introduction might not have meant too much to you. But think of it as diffusion is a process of guided transformation of noise into a shape. Whether it, in the case of images, computer vision, it's a picture. In the case of text, is into something. So here what you're trying to do is, let us say that you're basically saying that I can start with a random vector with random numbers, and successively I can keep moving it to finally end up with the context vector. So suppose I'm given the context vector C0 all the way to Cn minus 1. So actually they use X for it, for all the context vectors. So let me also use X. So these are the actual consequent vectors coming out of the sonar and the transformation. So what you're basically saying is, what is this? can I produce it from noise, from vector that comes out of noise, transform noise into the next concept, conditioning on this by listening to the prior sequence of concept vectors, or prior, in other words, the prior sentences which have been transformed into concept vectors. And that is classic reverse diffusion process. You can do that. And so what it becomes is, you can continually do that. And the way they do that is, they have, and there's a bit of nuances, they have something called a one tower and two tower approach. In one tower approach, the transformer decoder is, and the denoising step, both are done by the same transformer. Like, because see, at the end of the day, the diffusion models internally use a transformer. So you can do all of it within the same machine. But in the case of a two tower approach, which is more robust, but computationally heavier, what you do is you use you use two different things. You use one tower for denoising, or the diffusion part, and one for the sort of the decoding part, right? So you take a two tower approach, and they mention that one tower is computationally more efficient. Two tower is better though. So in the, you have a contextualizer and a denoiser separately, right? So here it says the first model, actually, let me get to the highlighter. A first model labeled takes an input context vector, that is the so far vectors, and causally we apply a decoder only transformer with self-attention. So this will produce you the next. The output of the contextualizer is then fed to a second model dubbed denoiser, which predicts a clean sentence embedding by iteratively denoising the latent this. So the denoiser consists of a stack of transformer blocks with cross attention to attend over the encoded context. Both the denoiser and the contextualizer share the same transformer hidden dimension models and so forth. So these are obviously technical details, and not something one has to read a little bit more carefully to see it, but it's straightforward. What they're basically saying is that we are going to use both aspects, the standard transformer decoder and the denoiser, denoising part of the diffusion approach, and together we'll do it. There's a third approach, which is a quantized LCM. It just basically says that texts have a discrete representation. Because they have a discrete representation, so you can take a more quantized, that it should pick from, and not predict any vector, but it should predict one of a finite set of vectors. The space is quantized, the embedding representation space is quantized. And how do you do that? Well, quite simple. You quantize the sonar space itself. Right? Those of you who are familiar, for example, of the vector quantized autoencoder, VQ-VAE, this would be somewhat reminiscent on that, even though this one uses actually improved residual vector quantization, a slightly different thing. Actually, no, I take that back. Vector quantized uses a code book, whereas this is more simple quantization, granularity quantization. They just use, we use FAS implementation, which performs iterative k-means clustering of the residuals and so on and so forth, etc. So some form of quantization, right, that they use. We train the RQV code book on 15 million English, blah, blah, blah. And you come up with 8192 unit per code book, which is it. So the ideas are very similar, actually. But yeah, there are slight nuances. So anyway, this paper goes on, and it shows that the results are pretty good. But I would like to summarize, since we have been going on for some time. What are the main ideas? The main idea is that let us not deal at the level of the token. Let's break up a text into concepts, a sequence of concepts. Let's go into the embedding sentence space, concept embedding space, and do the next concept prediction, not next token prediction. If we can create a good engine for the next concept prediction, which is why they call this whole paper large concept model, then from the next concept that you have predicted, you can always decode it to a sequence of tokens. So you will produce a whole sequence of tokens in this approach. And that is essentially the whole paper. It's a long paper. There are many, many nuances to this paper, but these are the main ideas that that are there in this paper. So that is that, guys. Any questions? Was it clear, guys? Was the main idea clear? Anyone? Everyone is quiet. So I don't know, is there something being said in the chat? Maybe, let me see, where is the chat? All right, I'm not getting any feedback. So
so you said that this is language independent.
that is right.
So when you say language independent, when
Yes.
it will convert into that particular language after all the process is over?
That is right. Look at this. Look at this picture. Your output is concepts, isn't it? And now the concept decoder, in this particular case, basically your sonar decoder, all it needs to do is you need to tell it which language do you want to decode it into.
I see. Okay.
Right? And so this has to do with sonar. Sonar is actually an amazing text encoder that covered 200 languages. It was considered quite a feat, actually, that with almost equal facility, it dealt with resource-rich and research-poor languages just as well.
Thank you.
So that facility comes from the sonar encoder. What it is saying is that, see, that this machine works only at the level of concepts. But because the concept can be decoded not only into languages, any language you want out of the 200, or any modality you want, speech or text, therefore, you can have English text go in, and let's say hypothetically, you can have French voice come out.
I see. Okay.
Right? That's that. Because once it becomes concepts, the large concept model in the center, it has no idea where exactly that concept came from. It doesn't know whether it came from text or it came from audio. It doesn't know which language it came from. It deals with the abstract concepts, right? The semantic essence of that text, of that sentence.
So even here, there will be some kind of hallucination or errors, or will it be less when compared to what
See,
is done in
I
word
think,
tokens?
yeah, I think they talk about that somewhere. Let me see, where do they talk about it? I forgot. Um, they talk about it. Hang on, let me go and search for it. Hallucination. Hallucination. Okay, they don't talk about it, but here is here is my guess. See, if you look at hallucination, people have often observed that hallucination begins when you do sampling of the softmax, and you end up picking a token associated with which the confidence is low. If you look at the entropy coming out, information entropy of the sequence of text, you can see that the confidence is dropping. Right? It's an observed fact empirically. And it has to do with the fact that once you predict a couple of wrong tokens, or you pick a low confidence tokens, you can drift in the direction of hallucination pretty quickly. Right? To the extent that this deals at the level of concepts and decodes concepts, right? I would imagine that subsequent work will show that there is a significant improvement when it comes to hallucination.
Mm-hmm.
It is far less likely that you would hallucinate within this. But then you can ask, well, okay, we can stop hallucination even in a LLM. Just don't sample. Just pick the highest probability token and produce it. it becomes a deterministic machine at that moment, right? Problem in LLM has been that when you make it a deterministic machine, when you just pick the highest probability token, then the output is bland and boring and repetitive. So the question you can ask is, will that same thing not happen for concepts? That the next concept prediction? And the answer to that is, it won't happen because when you use a diffusion model is inherently stochastic, right? So given the same text, for example, with images, if you play with DALL-E or anything, you give it the same prompt, and every time it will generate a different image, right? Any image whose embedding vector is proximal to the text embedding vector is a perfectly good image. And there are infinitely many of them. And so variety or diversity of responses comes within this space, because it will not generate exactly the same concept. It will generate within the neighborhood some concept, and there is still variety there. But though the variety, because it's in the neighbor, it is with concepts, one would imagine that it's a little bit more readable, more coherent when it comes out. That's the main idea, I think.
Thank you.
All right, folks, any other questions?
Yeah, this is Alan. So at the beginning, I thought when we're talking about concept, looking at this paper, I thought the concept is at the level of the meaning of words or the meaning of sentence. But when we look at, for example, figure 1, it more indicate the concept meaning human thoughts, how people think, instead of the meaning of language. Now, my question is, for language, for example, if we say English, the meaning of language is uniform, meaning if you are older people, if you're younger people, if you're different people, you say the things in the same way. The language always means the same, no matter who is saying it. But if we talk about how humans think, people's thoughts, then say the generation gap, older people, younger people, man, woman, it may think differently. So if the concept is really meaning the thinking of people, then could this concept encoding, concept decoding present difference if you are referring to different people, for example, older people, younger people, men, women, where people think differently instead of how the meaning of language?
Yeah, Alan, I think I get your question. So first, a clarification. See, they start with the abstract notion of a concept, right? Which to me is that one thought. So what they are saying is human text or human speech is a garland where each beat is an idea or a concept or a thought. Right? Then what they do, if you look at figure 1, they say that for the sake of this feasibility, this a proof of concept paper, just to see if the idea is feasible, they now reduce it down to the most trivial implementation you can have. They are saying, okay, for the sake of this paper, we will consider short sentences as a concept. So we'll break a text into short sentences, and each short sentence is a thought, is a concept. Right? So therefore, a text is a sequence or a garland where each beat is a sentence which has been encoded, right? A concept. A concept and text therefore become synonymous. To your question, see, the young and the old, they think differently, but my way of saying it would be that they create different garlands from the same beat when they are talking about something. They approach the problem differently. They say different things. So they differ in the overall text. But a sentence, whether it says Tim wasn't very athletic, maybe that would be our generation saying, well, Tim wasn't very athletic. And a younger kid saying, oh gosh, Tim sucks at athletics. Nevertheless, both of those two sentences would map to the same embedding in the embedding space, to the same vector, hopefully, or similar, not same, but proximal vectors in the embedding space.
Yeah, thank you. I get you what you're saying. Thank you.
Yeah, and also they do mention in this paper that, see, they took at the level of concept, but there is a more granular way of looking. What about a paragraph or a theme? And they say that that remains work to be done in the future. That can we, instead of predicting the next sentence, can we predict the next paragraph itself, the topic of the next paragraph itself, or the next theme itself, the next section in the document? And they raise, therefore, some very interesting concepts like that. That if I tell you, for example, that these are the themes, what would be the next theme, most logical next theme to discuss, right? And they posit that this approach perhaps is extensible to those situations also. So, all right, folks. So, in that case, I wish you all again a very happy holiday season and a very happy, really very happy and successful new year.